My name is Lu Liu from Dalian University of Technology. I'm very glad to introduce our work here. My topic is discrete element analysis of ice load on marine structures with dilated polyhedral element. This is the outline of my presentation. First, let's see the motivation. The background of our research is the ongoing development in the Arctic area. Research that related to our work includes the offshore structures in ice-covered regions, structural analysis, and design of icebreaker, and cargo voyage in Arctic routes. The oil development in Bohai began at about 1960s. The ice floes on platforms, ice-induced vibration influence the operations and safety of oil platforms in Bohai. Now there are more platforms in the Arctic area, such as the concrete platforms of Russia, and people may know more about Kulluk, Molipek. There are some open data and report about the ice load and ice conditions in the Arctic. They are quite useful to our current study. The icebreaker is very important for explorations and development of the Arctic. The scientific investigation, Arctic shipping, rescue missions in ice-covered sea, and ice management for marine platforms demand icebreakers with good ice-breaking performance. Studies about ship-ice interaction, ice breakage, structural damage and design, ship stability in ice region attracts a lot of attention. China deployed a new icebreaker Xuelong for the scientific expeditions in polar area. There are a lot of engineering problems that are waiting to be answered. The Arctic shipping routes, northeast routes for Pacific, can save about 13% mileage of traditional shipping routes between East Asia and Europe. There are more and more cargo ships navigating the Arctic routes, and the voyage requires the escort of icebreaker. But the ice load and the resistance on cargo ship during escort need to be studied. Model test, field test, and numerical methods are commonly used approach to study the ice load on marine structures. Comparing with the model test and the field test, the numerical method is economic, and the conditions can be controlled precisely. Numerical methods such as cohesive element, finite element, and pure dynamics have been used. DM model is quite popular in rock and sand simulations. It's been acknowledged as an effective approach to analyze the breakage of brittle materials. DM is also widely used to simulate the fracture of sea ice in engineering. The ice load on marine structures, such as offshore platforms and vessels, can be determined with DM for structure design and safety analysis. The spherical and polyhedral elements are the most used element shapes. Spherical element has easy fundamentals and has advantages in simulating small ice fragments. Polyhedral element is more similar to the real ice blocks, but its efficiency is lower. But in DM model, how to model the breaking process of sea ice, how to consider the complex conditions in real scenarios. Validations and computational efficiency should also be considered. The dilated polyhedral element is used in our DM model. I'll introduce the details of the method. The dilated polyhedral element is the Minkowski sum of a dilating sphere and a pure polyhedral. With different sphere and polyhedral, different shaped dilated polyhedral can be obtained. We can see the ice shape in nature looks like rounded polyhedral. It is similar to the dilated polyhedral. The motion equations of one dilated polyhedral is solved on its centroid, including transition and rotation. The rotation is solved with the continuum. The forces that acting on the centroid including contact force, bond force, and hydrodynamic force. We will introduce the DEM-SPH coupling model in the next section. The hydrodynamic force will be replaced as the interacting force between DEM and SPH if liquid-solid coupling is considered. The most cumbersome part of DEM is the contact detection between elements. Here, an approximate envelope function is employed in the contact detection between dilated polyhedral elements. There is a smoothing coefficient k in this function. Different shapes from sphere to a shape that is similar to the dilated polyhedral can be obtained with different k. With this function, the contact detection for the contact center can be regarded as an optimization problem. This optimization problem is solved with the Newton-Raphson iterations. And during the iterations, the smoothing coefficient k changes from 1 to 0.001. This can guarantee that the element shape is close to the dilated polyhedral. The contact force model used here is based on Hertz's contact force model because the dilated polyhedral has special geometric features. Here, there are two different ways to calculate the contact force in fact. The simple one is to directly calculate the contact stiffness based on the elastic modulus, Poisson's ratio, and the equivalent radius of adjacent elements. The other way is to calculate the contact stiffness according to different contact type, like sphere-sphere, sphere-face, sphere-cylinder, cylinder-cylinder, cylinder-face, and face-face. Then the curvature radius on the contact point will be considered in the calculation of contact stiffness. I haven't studied the specific difference to the results between these two ways, but I think the simple way seems more stable and efficient in my opinion. The bond failure model is employed to consist the continuum with dilated polyhedral element. The bond model is based on the rigid spring element. The spring element is added on the interface between adjacent elements. So the strain and strains between elements can be calculated, and thus the bond force can be calculated. In the failure model, an elliptic equation is used for the strength criteria, considered the normal and shear strength. The traditional strength criteria may determine in tension and shear separately. It will be determined as failure if tension or shear is larger than the strength, just like the dot line in this map. But with this equation, the bond will be easier to be failed. Besides, the Moore-Colombo law is used to calculate the shear strength. Accordingly, the equivalent strength and strain can be calculated. Here, the stiffness softening is considered by calculating the damage coefficient to correct the stiffness. The final failure of the bond is based on the BK model of fracture energy. The hydrodynamic force includes two parts, buoyancy and drag force. Each element phase will be measured as triangles so that the volume that immersed under water can be calculated, and then the buoyancy can be calculated. The drag force is based on Sun and Shen's work. The breakage with bond failure criteria occurs on the interface between adjacent elements, or we can say the crack is preset. We developed a particle breakage model that allows elements to directly break into several fragments. Sometimes we call it subbroken. Of course, it needs a strategy to reconstructing the geometric shape of element. The stress in one element must be obtained to decide the breakage and crack direction. Here we tried two different approaches to calculate the stress inside an element. One employs the Cauchy strength tensor for granular materials. The principal strength and the direction can be determined. The von Mises strength is used to determine if breakage occurs. Element is cut through its centroid by two perpendicular planes that are parallel to the second principal strength, and form a 45 degree with the fourth principal strength. The other approach calculates the strength on randomly distributed points inside the element with 2D Flamant solution, because the ice can be regarded as a plane strength problem. The breakage and crack direction are similar to the first approach. Okay, I'd like to introduce the liquid-solid coupling of DEM SPH model. Here the liquid is seawater in fact, and solid includes sea ice and marine structures. Here we use the EI-SPH to simulate the seawater. EI-SPH is explicit incompressible SPH. Traditional SPH uses equation of state to calculate fluid pressure with density, but EI-SPH uses an explicit scheme to calculate pressure with the pressure Poisson equation, and it considers the incompressible condition. So EI-SPH is more suitable than traditional SPH for incompressible flows. Another problem of using SPH is how to calculate the interaction between solid and fluid. The mostly used way is to construct the solid boundary with fixed or ghost particles, but this way requires a lot of work on how to construct the different shape of solid boundary with particles, especially for complex shaped solid boundaries. Obviously, this way is not suitable for the interaction between water and many ice elements. Here we fit formulas with fixed particles and use the formula to calculate the interaction in the simulation without the fixed particles. So the interaction between fluid and solid can be directly calculated with the distance between them. Besides, a repulsive force model is also used to prevent unphysical penetrations. To validate this model, the hydrostatic pressure and dam break are simulated. The hydrostatic pressure is the same with the analytical solution. The front position and the shape of the free surface are compared with other people's work. Both of them have good agreements. To validate the DEM SPH coupling model, the dam break flow on the cubes is simulated. The position of cubes and the simulation snapshot are compared with the experimental data. Both have good agreements with other people's work. There are several simulation examples with the above numerical models. Some of them are for validation and some are for applications. Kulluk is a floating platform that are deployed in the Arctic. The interaction between Kulluk and broken ice is simulated. The ice element is unbroken, which means the bond failure model or particle breakage model is not used here. The ice force on Kulluk is obtained and analyzed. The ice force is compared with the field observation data under different ice concentrations and ice thickness. The field data include kinds of complex conditions, include quite fierce ice conditions. So the ice force or field data is in a quite wide range. But the simulation results agree with the field data, including the changing trend. The ice load on conical pier in level ice is simulated with the bond failure model. BF model means bond failure model. The average force of DM and Bohai results are in good agreement under the same condition, although the standard deviation are different. Here is the simulation case that both bond failure mode and particle breakage model are implemented. PB model means particle breakage model. We can see that the ice has better breakage shape than that without particle breakage model. The ice force of DM is compared with field data of Bohai C and ISO standard. Both show good agreements in trends. Here is a case that uses the particle breakage model with 2D Flamant solution. The stress map of sea ice can be obtained. The ice load iceberg or 雪龙 in level ice is simulated with DM model. The ice resistance on the ship in DM is compared with the Lindquist formula. The mean peak force and the mean force are counted. This is the submersion of ice fragments and the different ice thickness. The ice fragments moving from bow to stem, and the submersion is serious when the ice thickness is larger. The line loads along the ship profile on the waterline show that the largest local load is at bow stem and ship shoulder. Especially the ship shoulder, it bears a squeeze from both sides. We have field data of 雪龙 that monitoring the local line load at bow. The comparison between the maximal value from DM and field data shows good consistency. But only 3 cases are used to compare for now. This is a simulation with bond failure model and particle breakage model. The ice is modeled as a big ice floe. The ice breaking pattern is okay, we think, but the ice resistance seems not good enough. This is a simulation with these two models, but the particle breakage model uses 2D Flamont solution. On the contrary, the ice load shows better, but the ice breaking is not good enough. We are still working on this problem. The escort of icebreaker for a cargo ship is simulated. The ice resistance is analyzed. Here we study how much ice resistance on the cargo that the escort can reduce under different conditions. The force reduction rate is defined as 1 minus the ratio between forces with and without escort. It's interesting that the rate decreases first and then increases when the ice thickness increases. This is a modeling of the ship in DM-SPH simulation. Traditionally, the ship hull is measured as triangles to detect collision with SPH particles, but it costs too much time and there are still some problems in this method. Here we use the level set method to model the ship. It is more efficient and stable. This is a DM-SPH simulation that ship navigates in broken ice field. Different with the ship in level ice, the local load concentrates in the bow post. This is in level ice, but in this case we add a local FEM model in ship bow. It is just a quite small part, but this allows us to study the structural deformation and stress. This is our current work on this topic. There are many works need to be studied deeper, such as validations, and some models are alternative, but which one is better? And what about the advantages and disadvantages? So that's our future work. Thank you.